Hello. It's a rainy day in Kirksville. I'm down in the basement, and I'm going to do a series of little tiny videos to show you how the RC filter circuit lab for intermediate physics lab, how that works. This first little video, I just want to say a few words about the circuit. So if you take some kind of a voltage source and you hook it to a circuit, if that circuit is two circuit components in series, then what happens is the voltage from the source divides up between the circuit elements in the series circuit. So for example, if the two circuit elements are resistors, you should know that the voltage divides in proportion to the resistors, so the bigger resistor gets the bigger share of the voltage supplied. And for resistors, you get the same law whether it's AC or DC voltage. In today's lab, though, we were interested in looking at a resistor in series with a capacitor and how that circuit behaves. And in that case, the interesting stuff happens with AC circuits. First, consider what happens with a DC circuit. So you have a resistor, a capacitor, and a battery, essentially, and you hook them all up in series. Essentially what happens as soon as you hook it up is that for a short period of time, current flows through the resistor and charges up the capacitor, but in a pretty short time the capacitor gets full and the charging stops. And so now, since there's no current through the resistor, remember Ohm's law, V equals IR, no current, no voltage drop. So if you hook an RC circuit up to a battery and wait long enough, there'll be no current, the voltage drop across the resistor will be zero, the capacitor will be fully charged up to the same voltage as the source, and remember, for the capacitor, Q equals CV, so more charge, more voltage drop. Okay, so now imagine taking that circuit and hooking it up to an AC circuit. If it's an AC circuit and it's very low frequency, you might imagine that it's pretty much similar to the DC version, namely that the capacitor has plenty of time within the cycle of the source to charge up and discharge, and so it pretty much keeps up with the source and charges up fully. And so for the most part, for low frequencies, a lot of voltage appears across the capacitor. It doesn't take a lot of current flowing for that to happen, so there's very little current flowing, and so there's not much voltage across the resistor. On the other hand, if you go to high frequencies, now the capacitor can't keep up, and so you're trying to charge and discharge the capacitor rapidly, but it takes time to charge up the capacitor through the resistor, which sets the flow of current. And so the capacitor never has enough time to get much charge. It never has much charge, therefore it never drops much voltage. There's a lot of current flowing back and forth in the resistor, so most of the source voltage appears across the resistor. At any time, Kirchhoff's law holds, so the voltage drop across the capacitor plus the voltage drop across the resistor is equal to the voltage drop of the source. So at low frequencies, most of the voltage is across the capacitor and very little is across the resistor, and at high frequencies it's the other way around. Most of the voltage appears across the resistor and very little across the capacitor. So I guess the last question is, where does that transition take place? At what do we mean by high frequency and low frequency? And for that we define something called a break frequency, and it's related to the fact, as you remember, that the product of R times C gives you a time. It's called the RC time constant. And it basically talks about the timing, the exponential time scale of charging and discharging a capacitor when hooked to a DC circuit. Well, the inverse of that time is an angular frequency, an omega, and that's the break frequency. And then, of course, omega equals 2 pi f gives you the break frequency in hertz. So that's sort of the basic background, and now I'm going to pause the recording and set up another recording where I can show you some of the equipment and how it's hooked up.